Okay. Okay. All right, so let's see. What do we have here? We've got our... we look at this, and we know for certain this is not elastic. This collision is not elastic because the bullet goes completely through that whatever it is, pendulum bob, and comes out the other side, and it leaves a hole in it. That's a huge amount of deformation, right? When there's not a hole in something and then there is a hole, right? You've broken bonds, you've pushed stuff out of the way, lots of friction when that bullet goes through the pendulum bob, lots of friction. So a lot of our mechanical energy is going to be converted into other kinds of energy that we can't account for anymore, right? This is not elastic. We can't use energy just to solve this problem. We have to kind of break it up. I like to make a timeline. But we do know that there's a collision involved, right? There's a collision, and when we see a collision, we should always be thinking momentum. All right, so let's make a timeline. So this is going to be, let's see, our starting point is just before the collision. We've got I'm going to call that V1. The pendulum is at rest. Then we want always want the split second before the collision and the split second after the collision as two of our times on our timeline. I've got the split second before the collision. The split second after the collision looks like this. We've got our it's the same size, it didn't grow. We've got our pendulum, but now there's a hole in it, right? And it's moving with speed v2. And our bullet has come out, and it's moving with speed v1 over 2, half of its initial speed. And then we've got some later time. The bullet is just doing its own thing. It's still moving at the same speed. We don't really care. And our pendulum bob has swung up to its highest point there. So a little bit of maybe a confusing point here is that that pendulum is attached to a solid rod. As it swings around, it cannot fall in to a smaller radius because there's a rigid rod holding it up. So this really isn't a circular motion problem. If it was a string instead of a rod, the mass at the end would have to have some velocity, right, as it comes around in order to keep the same radius. If it didn't have any velocity when it got to the top, it would fall in. But because there's a rigid rod there, as it comes up to the top, the rod will hold it up. So the minimum speed to make it over occurs when it gets to the top and it just comes to rest at the top. It just has zero speed at the top. Anything more than that would cause it to go over, right? So we're going to say V equals 0. This is going to be V3, right? So this is time 1, this is time 2, and this is time 3. Now we'll work backwards. We'll work backwards, and we're going to find the incoming speed set of the bullet such that this pendulum bob just barely makes it over the top. So we're going to go from, let's see, we're going to go from 3 to 2 using energy. And that's going to tell us what V2 is. And then we're going to go through the collision. We always use momentum to get through the collision. Okay, so the energy at 3 is equal to the energy at 2, because you can set up the equation more formally if you like. There's E initial plus work done by friction plus work done by external equals E final, right? That's kind of our equation. But I can see right here I have no friction and air resistance. I'm ignoring air resistance and friction. I just have a pendulum that swings up and down, right? That's all I care about is the pendulum. What's happening to the pendulum between time 2 and time 3? Because the bullet, nothing happens to the bullet between 2 and 3. It has the same energy at 2 as it does at 3 as it does way later. So all I care about is the pendulum. At 3, all the mass is up at the highest point and the velocity is 0, so it's all gravitational energy. It's UG. And at time 2, it's all kinetic energy. It's at its lowest point, it's all kinetic energy. So we have 1/2 m pendulum V2 squared has to equal m pendulum G H. The mass of the pendulum cancels out. We get our velocity is the square root of 2gh. And what is h? H is the height that the pendulum went up. So that's this distance here. It went from here to here. That's 2 times the radius, or what did they give us? 2 times the length. I guess I'll write 2L. Where this is L. Okay. Yeah, the energy at time 2 is all in the form of kinetic energy. And the energy at time 3 is all in the form of gravitational potential energy. So now we're ready for our momentum equation. And if you don't see this, if you just see a problem like this, you're not sure where to start, always start the split second before and the split second after the collision and use momentum to get through the collision. So write out the momentum equation. So I would have the momentum at time 1 has to equal the momentum at time 2. I'll call the right my positive direction. At time 1, I only have the bullet moving, right? The pendulum has no momentum. And at time 2, they're both moving. I've got the mass of the bullet. I've got half of its velocity in the same direction, so positive. It's still going in the positive direction. And then I've got the mass of the pendulum times its velocity. So you write out this equation and you say to yourself, well, this is only one equation, but I have 2 unknowns. I have V1 and V2. I can't figure that out with one equation. With one equation, I can only have one unknown. So then you start digging into the problem. Is there some information that's given that I'm not using that would help me figure out what one of these missing variables is? And yes, there is. There's information that helps us find V2. and then you go and dig in, right? That's a technique for finding things if you're not exactly sure where to start. Pick something that you know. Oh, there's a collision. I can get through that collision with momentum. And then you write out the equation and see what's missing. Okay, let's plug in for V2. We've got the square root of 4GL. We know all the masses, right? Lowercase m, capital M, and yeah, so we can solve it now. We're basically done. As soon as we plug in this value, we're done. So this is going to be this one minus a half, right? So this is going to be MB V1 over 2. And this is going to be MP 4GL square root. We could take the 2 out if we wanted to. And we're solving for V1, right? Okay, and if we wanted to, that 4 comes out of the integral as a 2. Doesn't really matter. 2 times 2 is 4. Okay, questions on this one? Okay, center of mass. We've got a rod with one end at the origin. We'll pick some little tiny chunk of the mass and call it dm. And that little tiny chunk is so small, we can treat it like a point mass. This is a distance x, and this is a length dx. One thing we know is the total mass is equal to the integral of dm. If we add up every little chunk of mass, we get the total mass of the rod, right? So we'll do this first. And what is dm? dm is the density multiplied by dx. And the density was given. And it's in meters. Oh, but lambda's in grams. Okay, grams. And our limits of integration, 0 to L. We're integrating over the whole length of the rod. So 0 to 0.3, because it's in meters. X has to be in meters. And where am I? I get 50x plus 20x squared over 2, evaluated from 0 to 0.3. That's 15 plus 10 times, that's 0.9, is it? Minus 0. I think I got 15.9. And this is in grams. Let me know if I did that right. I'm trying to do this in my head. I guess you can do the integral however you need to. I mean, the easy ones, it's quicker just to do it in your head, right? If it's complicated, if you have something really complicated, I've got some integrals on the formula sheet, or maybe not for this class because you don't need them. For 4b, I definitely have some integrals on the formula sheet. We have some tricky integrals there. I just put them on the formula sheet. All right, now we want to find the center of mass. So the center of mass is the integral of x dm over the total mass. So since we just found the total mass, I guess we don't have to do that again. We'll just divide by 15.9 grams at the end. The integral of x dm is going to be 50 plus 20x x dx, right? From 0 to 0.3 over 15.9 grams. And this is going to be, what is this going to be? 50x squared over 2 20x cubed over 3 and you can plug in the numbers and see what that turns out to. Okay. We all right with this one? If lambda is constant, you just plug in total mass over total length, right? If lambda is not constant, you plug in whatever formula you're given. Okay, we've got a wooden block resting on a table over a hole, 5-gram bullet, fired upward, stick together. All right, so again, we know immediately this is not elastic because these two objects stick together, right? They become one. So lots of energy is converted into things that we can't account for anymore. Friction, heat, deformation. We will break it up. We'll make a timeline. Just before the collision, actually, that's the condition they've given us here. Just after. And later. And we'll call this time 1, time 2, and time 3. And we're trying to find that height, I believe. Oh no, they give us the maximum height. We're trying to find the speed of the bullet. So it's like a ballistic pendulum problem. Exactly. Okay, so we're working backwards trying to find V initial. We're given the masses. We're given the height that the thing goes up. So we'll work backwards. We'll go from 3 to 2 using energy. And we'll go from 2 to 1 using momentum. Always go through the collision with momentum. Correct, no height change yet. At time 2, just after the collision, it hasn't really had a chance to go up yet. It's that split second after the collision before it started to go up. No height change. So the energy at 3 has to equal the energy at 2. At 3, it's all gravitational potential. And at 2, it's all kinetic. And in between, we don't have any friction. We don't have any external forces acting on it. So we can just say gravitational energy, M. And it's M of everything, right? The bullet plus the block, both. GH, and this is 1/2 M of everything, V squared. And the M's cancel out. And we get our velocity at time 2 is the square root of 2GH. And H was given. Okay. Then we go back to our equation, our timeline. And we do momentum. Momentum at time 1 has to equal the momentum at time 2. I'll say the right is my positive direction. At 1, oh sorry, up is my positive direction. Forgot which problem I was working on. At time 1, only the bullet has momentum. The block doesn't have any. And at 2, they're stuck together. And now we can solve for V1. V1 is just you bring the bullet, the mass of the bullet to the other side there. Okay, and oh, V2 we know. There we go. Okay. A bullet into a block. They stick together. Lands 2 meters. Determine the speed of the bullet. Another type of ballistic pendulum, trying to find the speed of the bullet. This time you can use some of your kinematics equations, right? So I would do a timeline. We know that this force certain, inelastic, because they stick together. So we're going to have to break it up, use different techniques. In this case, we're not using energy, we're using kinematics as our other technique. So momentum to get through the collision, and then kinematics to figure out, or vice versa. I think we're working backwards through this problem. So you're going to go from 3 to 2 using kinematics equations, and then you're going to go through the collision using momentum. So your kinematics Y is going to give you the time, and X is going to give you the velocity from the distance. So we'll pick, where do we want our 0, 0 to be? How about we'll let this be our origin, and our positive directions will be up and to the right. So its initial y is h, and its final is 0, and h was given, right? Height of the table, 1 meter. And we know the initial velocity in the y direction is 0. Final velocity, we don't know and we don't care. Acceleration is 9.8 meters per second squared in the downward direction. So we said up was positive, so that's negative. So we should be able to solve for t. Using an equation that's missing v final. So that would be, what would that be? Y final is y initial plus v initial t 1/2 at squared. V initial was 0. That's nice. We don't have to solve a quadratic. So we've got time. Plug that into our x direction. And we know we go from 0 to d. So the x direction says velocity is distance over time. plug in the distance and the time, and you get the velocity. So now we know v, what is this? This is v2. v2, yeah, now we know v2. And we use momentum. So the mass of the bullet times v1. The block is just sitting there. It doesn't have any momentum initially. At the end, they are stuck together. And solve for v1. I don't think you can use conservation of energy because you're going to find the total velocity, right? You want the velocity in the x direction, not the total velocity. Okay. V2 is V initial x, yes. I'll write that there. Thank you. V2 is V initial x. Okay, we've got a firefighter sliding down a pole, constant friction. And then she collides with a 20-kilogram platform and then compresses a spring. So here we've got stuff happening before, stuff happening afterwards, right? So our timeline, maybe I should read the whole problem first. What does it say? Okay, yeah, so our timeline is we have a firefighter up here. That's a firefighter. And at rest, right? This is earlier. I'll call that time 1. And then we've got this platform here on a spring. Then at time 2 is just before collision. So our firefighter now, oops, went a little too long on that one. Our firefighter now is here, moving with speed v2, just about to collide with that platform. And 3 is just after the collision. They are moving together. And 4 is later. And they've come to rest. Zero Right? That's the maximum distance the spring is compressed. Okay, we good? It's all clear with my expert artistic ability. So we'll work our way through. We know we're going to use momentum, right, to get through here. And we can use energy here. And we can use energy here. But we can't go from the beginning to the end with energy because there's this collision in between. And here they stick together. We know that this is inelastic. But even if the firefighter bounced off the platform, we wouldn't know unless we were told, right? Okay. What are we doing? We're trying to find the final spring compression at the end, right? So going from 1 to 2, energy at 1 is not going to equal the energy at 2 because there's some friction now. Energy at 1 is all gravitational. And at the end, it's all kinetic. So we have m, g, h minus the friction force times h, 1/2 m v2 squared. We're trying to find v, right? So we can multiply by 2 and divide by m. We're given those other things, right? So we've got 2 times gh minus the 2 times the friction force. So anyway, plug in the numbers. You got V2 now, right? They gave you the friction force. So all you had to do was multiply that by the height of the pole, the distance that that force acts on our firefighter as she slides down the pole. Now we go through, we say the momentum at time 2 has to equal the momentum at time 3. I'll pick down as my positive direction. So I've got the mass of the firefighter times V2 plus 0. The platform is not moving at all, right? And then afterwards, they're stuck together, right? Mass of the firefighter plus the mass of the platform times V3. Plug in V2, solve for V3. And now we can use energy again. Energy at 3 has to equal energy at 4. We don't have any friction this time, no external forces. At 3, it's all kinetic energy, right? And at 4, it's all spring potential energy. So we have K3, 1/2 m both, right? Both v3 squared, and this is going to be 1/2 k is the spring constant, x squared, and we're solving for x. X is this distance right here. The spring compression distance x. So you've got a square root of k over m, sorry, m over k. K is the spring constant. Halves cancel, times v3. Okay. Any questions? I think we're done with the problems I sent out. But I felt it was necessary to send those out because our book is so deficient in problems like this. You'd really need practice setting up that timeline, knowing when you can use momentum, or I should say when you have to use momentum, and when you have to use other techniques that we've learned, and work your way through the problem by breaking it into smaller problems. Hopefully this helps a little bit. Work done by spring. Yeah. Got it. Work done by a spring versus spring energy. So that is, it depends how if you're using the overall energy conservation approach and you include the spring in your system, then we don't have external work done by the spring. We have transfers of energy within our system, which we account for using potential energy terms. So spring potential energy is always positive, 1/2 k x squared. The distance the spring is stretched or compressed is x. K is the spring constant. Always positive. But the work done by a spring, it has the same formula, 1/2 k x squared, because you have to integrate the force, right? Don't make the mistake of saying the work done by the spring is the spring force times the distance. What's the spring force? Kx. What's the distance? X. K x squared. That's not right. The spring force is not kx for the whole time, right? It starts out at 0 and it works its way up to k times x maximum. So when you integrate, you get 1/2 kx squared. But remember, the work done by a spring can be positive or negative. If the spring if we're sliding a block in one direction and the spring is pulling back in the opposite direction, it's doing negative work on the block. If it's pushing the block in the same direction it's moving, it's doing positive work on the block. So you have to look at the situation and see whether it's positive or negative. Does that help a little bit? You'd use work done if I asked you what the work done by the spring was. Or if you do not include the spring as part of your system. You have to define what's in your system. If you have a block being pulled a block being pulled to the right, and you want to include the spring in the system, which is what we would usually do, then you don't have external work done, right? You have E initial plus work friction plus work external equals E final, right? So what is E initial? Well, it's kinetic, it's gravitational, it's potential energy, it's spring potential energy. Right, that's what that is. Same over here. So if you include the spring as part of your system, then there's no external forces, you have U spring. If you do not include the spring in your system, then, oops, I didn't want to do that. Then you don't have potential energy stored in it because it's not part of your system, but you would have work done by the spring. See, it automatically shows up with the right sign on the right side of the equation if you use U spring. If you use work done by an external force, it's always on the left side of the equation. So you have to figure out whether it's positive or negative. Not that that's that difficult, but you have to figure out whether it's positive or negative. Make sure you get your sign right. If you use U spring, it either has it at the beginning or it has it at the end. It's always positive. It works itself out. The equation gets it right. Okay. Question about center of mass. Why isn't it L over 2 if there's non-uniform mass density? So if it's uniform density means you have a rod means the density is the same everywhere, uniform. That means if I cut a chunk out of here, whatever, 10 centimeter chunk out of there, and I cut a 10 centimeter chunk out of here, and I cut a 10 centimeter chunk out of here, they're all going to weigh the exact same amount because they all have the same length and they all have the same density. They all have to have the same mass. Right? Non-uniform. Oh, so where would we balance that? We have a uniform stick. Every chunk has the same mass, right? If we were to cut it up and weigh all the masses, they'd all be the same. Where would we balance that? If we wanted to balance it, where would we put our finger? At the halfway point, right? Half the mass on one side, half the mass on the other side produces the same amount of torque. It's going to balance at the halfway point. So the center of mass is at the center. Now we have a non-uniform rod. That means that if we cut a chunk, and we can make it non-uniform any way we want. Let's make, in class, the one we did was the right end was more dense than the left end, right? So kind of picture a baseball bat. What does a baseball bat look like? It has a thin handle, and it gets heavier, right? I've tried to make it kind of like a cone, but you get the idea. I'm recording this whole thing, so there'll be a video posted. I'll post the notes also. So if we cut a chunk out of this end, 10 centimeter long chunk, and we cut a chunk out of this middle, and we cut a chunk out of this end, all the same length, you can see M1 is going to be less than M2, is going to be less than M3. Now I know that this isn't a one-dimensional rod, a thin rod, but you can imagine we could make a rod with different materials along the length that made one end way more than the other end, right? So if we were going to balance this, where would we balance it? At the middle? No. The balance point would be closer to the heavier end, right? The balance point would be out here somewhere, right? Now this was one example, right? We don't have to shift the center of mass to the right. We could have had a formula, we could have had a rod, a non-uniform rod, where the left side was heavier. We cut a chunk out of here. M1 is greater than M2 is greater than M3. And where's the center of mass now? Center of mass is going to be shifted over here. It's always going to be closer to the heavier end. Right? I mean, the baseball bat just helps you picture what's going on, but really it's a one-dimensional thin rod. It's just that the density is changing as we move out, so that if we cut the rod into 10-centimeter chunks, the one out at the left side, in this case, is heavier than the one on the right side. Okay? Yeah, or we're changing the material or something like that, right? As we move out along the length of the rod, we're changing the material or somehow making it more dense, yeah. Exactly. Uneven distribution of mass, that's a good way of saying it. So work equals change in kinetic energy, right? The force, I guess technically you end up with a negative force. I think they're just interested in the magnitude of the force here. But the work is the force times the distance times the cosine of the angle between them, right, when you put their tails together. And this is going to give you a K final minus K initial. So if the object is slowing down, this force has to be doing negative work on it. But I'm pretty sure they just want the magnitude of the force. Did they ask for does the answer negative or positive? I would think they would just want the magnitude of the force. Yeah, well, work is a dot product. So it's force times the distance times the cosine of the angle when you put their tails together. That's where the negative sign comes in. Anytime the object is slowing down because of the force, that force is doing negative work on the object. Okay, that's what I assumed, you know, that I read this and I just assume they know, you know, that it's acting opposite the direction of motion, so it's doing negative work, but I think they just wanted the magnitude of the force. Is that all?